Dear students, good morning. I am Dr. R. Premshita. So we are the associate professor. I am going to start the design of reinforced concrete structure. Already we have seen the unit 1 first unit. Design of introduction design, working stress method, limit state method, classifications and the problem. Now I will start the second unit. Limit state design for bond, anchorage, shear and torsion. Along with this design of flanged beams, that means T-beam design, we will see. In this subject, what we are going to see means behavior of RC member, how in bond, what is the behavior of reinforced concrete structural member in bond and anchorage and the design requirements as per current code IS 416 and the behavior of RC beams in shear and torsion and design of RC members for combined bending, shear and torsion. The behavior of first we will see behavior of RC member in bond and anchorage. The RC beam is a composite material. We know reinforced concrete beam is a composite material. It is not made up of one material. Here we are using the concrete and reinforcement. So it is a composite material. It comprises of reinforced steel and concrete with proper bond. If this bond is inadequate, what will happen? If this bond is not proper, what will happen? Slipping of the reinforcement bar will occur, so which destroys the composite action. So the bond between steel and concrete can be achieved by the following method. How will make a reinforcement concrete proper bonding? Only first point, we will add chemical adhesion or frictional resistance or mechanical interlock. What is in the chemical adhesion? Cement is used as binder. As we all know, cement is one of building material. What is the purpose of adding cement? It acts as a binder, so which sets a hardened concrete independently and can bind other materials such as aggregate and steel together. Frictional resistance means friction between surface roughness of the reinforcement and grip exerted by the concrete. Then mechanical interlock, that means twisting or deformed bars can be used to increase the bond. Bond stress. What is meant by bond stress? Bond stress is developed at the interface of steel bar and the surrounding is known as bond stress. So where the bond stress occurs means the interface of steel bar and the surrounding. When this bond stress occurs, it is due to inadequate cover thickness and development length and reinforcement without L and U hooks and the lesser concrete grade. When it occurs means, so when this is insufficient, then bond stress will occur. Then slices. What is mean slices? When the available length of the bar is less than the length required, so the length of the bar we provided will be less than the length required, then slices are provided. Slicing can be done by one of the following phases: lapping of bars, welding of bars larger than the 36. When lapping of a bar occurs means we can provide slices, or which cases we can provide slices means welding of bars. When we increasing the length, we will adopt the method welding. So when welding of bar is we are providing means to increase the length, then bars larger than 36 mm diameter we provide slices. So mechanical connection. Next, when we using mechanical connection to increase the length of the bar, in that cases we can use slices. Next, shear design. We need to provide shear reinforcement in the beams. The RC beams are designed to resist. For what is the purpose of providing shear reinforcement? Means to resist the shear forces. That means resulting from external loads after determination of bending reinforcement. In the beam, combined action of and shear produces principal tensile and compressive stresses. When the principal tensile stress exceeds the tensile stress of concrete, formation of concrete, formation of crack occurs. So when the crack occurs means when the principal tensile stress exceeds the tensile stress of concrete means cracks will occur. So consider simply supported beam carrying the UDL throughout its length. The maximum bending occurs at a midspan where shear force is small at midspan. The principal tensile stress is equal to the flexural tensile stress. Because of that, flexural crack will be appear. So it is perpendicular to the axis of the beam at the midspan. At the same time, at the same case, bending moment is minimum at support, where shear force is maximum. So where the shear force is maximum means the bending moment is minimum near to the support. The principal tensile stress is nearly equal to the shear stress and is acting 45 degrees inclined to the axis of the beam. It is called as diagonal tension and responsible for the development of inclined cracks. Shear reinforcement are required near to the support to resist the inclined crack. So here what they are saying, what we are going to say is when the reinforcement is provided, what is the case we need to provide the shear reinforcement to prevent the diagonal cracks, inclined cracks due to shear stress. So as per code, critical section located at a distance B from the face of the support. For flexural member, shear force occurs at the face of the support and progressively reduces with increasing distance from the support. So inclined cracks do not develop near the face of the support and progressively reduces with the increasing distance with the support. So what percentage we need to increase the shear reinforcement? The 20 to 40% shear resistance by uncracked concrete, 33 to 50% shear resistance by aggregate interlock, and 15 to 25 shear resistance by the flexural reinforcement. Here you can see torsional reinforcement in design. When we need to provide torsion reinforcement. So what is the form of we will provide means the RC member is subjected to the torsion in combination with the bending and shear. The longitudinal and transverse reinforcement shall be provided. So the longitudinal and transverse reinforcement RC beams is the torsion. What type of torsion we can provide with two types, equilibrium torsion and compactability torsion. When we provide equilibrium torsion, statically determinate structure will provide the equilibrium torsion. The non-static indeterminate structure will provide the compactability torsion. And for T-beam also here classified as singly reinforced, doubly reinforced beam. So analysis of beams we have to do for singly reinforcement and doubly reinforcement. If you take singly reinforced beam, we have three conditions. That means for under reinforced also we need to design, and for balanced section also we need to design, and over reinforcement also we need to design. So for that we have different formulas to use to find out the sections. So here also we can use as per the first, if you take limit state method, the HU and HU limit is common. So HU is nothing but neutral axis, actual neutral axis, and the HU limit is the critical neutral axis. If the HU is less than the HU limit, then it is called as an under reinforced section. So for under reinforced section, there is a formula how we need to find HU. Before we are going to present this TB, and see here there is a two sections, the horizontal section and vertical section. This horizontal section we call as flange, and this vertical section we call as web. So this is called web. So the breadth we call as BF, it is denoted as BF, and this is the breadth of the flange, and this is depth of the flange. And this is called vertical portion. This horizontal part is called breadth of the web, and this is the breadth of the depth of the web. So if the reinforcement provided at the web means, then this is the tension zone and this is the compression zone. Here we will take two cases. First case we will assume the neutral axis lies within the flange. So whatever the problem, before solve, the first step is the case 1 we need to take, that is the neutral axis lies within the flange portion. So HU less than or equal to TF. The next case we have to take neutral axis lies below the flange. This is the case 2. So X is greater than TF. If XU less than or equal to TF means the formula is to find out XU. Then your second case to find the neutral axis, XU equal to 0.87 FY minus 0.45 FCK BF minus BW and 0.36 divided by 0.36 FCK BW. So how will you find out Y of means like this? All this formula is given in code book. We don't need to mark up. Only thing we need to keep in mind is to know for which case we need to adapt, then where we have to adapt. For the singly reinforcement means this is the formula I have to use, and for a doubly reinforcement, there is a different formula. The neutral axis lies within the flange. Same place we have to take neutral axis lies within the flange portion, and the neutral axis below the flange we need to consider. For that, this is the formula to find out XU in the W reinforcement, and XU there also you need to consider under reinforced section first. Then if it is the XU is greater than the XU limit, then we have to go for over reinforced section. So in this case, over reinforced the assumption comes that over reinforcement, then again we need to go over. We need to redesign. So this is the problem. Problem we will see later. So the theory part, what we saw in this classroom, we saw what is the torsion, what is the shear, and what is the bond, and why need to provide the bond. Bond. We saw then encouragement is what, then TB is TB. Okay. So here also you can see this shear. Here you can see all this formula in IS 456 page 76 class 40.1. So all this formula it is given, so you don't need to